Hello everyone, thank you for kindly visiting our paper entitled High-Resolution Graded Rainfall Dataset Derived from Surface Observation by Adjustment of Satellite Rainfall Product. Allow me to introduce myself. My name is Achmad Rifani and my colleague is Muhammad Reza Ferdiansyah. We both from Public Weather Service, Indonesian Agency for Meteorology, Climatology and Geophysics, Indonesia. This study is aims to provide high-resolution graded rainfall data that can be used for many purposes related with analysis to disaster mitigation. As we know, the rainfall observation is not distributed evenly, and the data derived from interpolation will result in a low reliability data, especially when there are only few to no observation point. Meanwhile, satellite-based precipitation products such as global satellite mapping of precipitation could capture better spatial distribution while having issues such as under or overestimations. We believe by combining both platforms, we could provide a high-quality precipitation dataset. The study is conducted over Greater Jakarta or Jabodetabek area, which spans from -6.8 to 5.9 south and 106.3 to 107.3 east. We use a 108-minute rainfall observation station provided by Tangerang Selatan Climatological Station and Bogor Climatological Station. And also we use GSMAP near real-time data with 0.1 degree resolutions hourly precipitations during January 2020, where several extreme rainfall and flooding events observed in Jakarta. The process in this study we applied is first we accumulate the GSMAP hourly rainfall data to 24-hour accumulation and then regrading the GSMAP data to 0.01 by 0.01 domain from its regular original grid, which is zero point 0.1 by 0.1 degree domain. And then we do spatial consistency check for the observation data, which following RIU 2020, we use the SCI index exceeding 6 for flagging the outliers from the observation data. And then we interpolate the observation data by using the radial basis functions following Hardy 1971 to 0.01 by 0.01 domain. And then we calculate the difference at observation points between the GSMAP data and the observation data. And then we interpolate back the differences to the domain by using the same RBF interpolations. And then we are adjusting the GSMAP data by that correction factor following FILA 2008. The result of spatial consistency check is removal of several observation points based on threshold used to maintain consistency between observation and GSMAP pattern, and avoiding extreme value appears from interpolation process. As you can see on the top row images, the localized slight to moderate rainfall is being removed from the interpolation after the spatial consistency check is performed. And also from the lower image, you could see the slight to moderate localized rainfall is also removed from the interpolation process after the spatial consistency check is performed. This is to maintain the persistence or consistency between the observation and GSMAP pattern. In this case, the rainfall pattern from GSMAP is only in south part of Jakarta, and the observation also shows the same area of precipitations, but more intense and more widespread. And then we present two examples of the GSMAP adjustment results. The first example is when there are several stations reports heavy to extreme rainfall event in Jakarta. The first case is major flooding in Jakarta, 1st January 2020. The adjustment results in shifting of heavy rainfall concentration area towards northeast. Meanwhile, the southwest part becomes more localized. As you can see that in the A part image, the blue colors in the different images means the satellites experiencing the overestimation of the rainfall. Meanwhile, the red area means satellite experiencing uh, underestimation of rainfalls. Adjusting the GSMAP data will result in more realistic spatial distributions of the heavy rainfall concentration area. And also for the second flooding case event on 24 January 2020, the adjustment results in more inland rainfall while maintaining rainfall over the northwest coastal area. The second example case is when there is only slight to moderate localized rain observations, which is not detected by the GSMAP. In the A part of the image, you can see that there is observed slight to moderate rainfall over the west part area. Meanwhile, the GSMAP could not detect the rainfall area. The adjustment of the GSMAP data results in more or better agreement towards the observation data. For the second case, on the B part of the image, you can see that GSMAP satellite does not detect any precipitation over Jakarta. Meanwhile, our observation confirmed that there is a slight rainfall over the north part of Jakarta and also on the southeast part of Jakarta. The observation does not remove because of after the spatial consistency check, this is not flagged as the outliers. So we preserve the data and use for adjustment to GSMAP data. The results is also better agreement towards the observations. For the validations, we use 11 stations as verification points, which is removed from the interpolation process to show the adjustment is successfully or not predicting the rainfall at that 11 stations. We calculate the domain-wide root mean squared error, which is performed before adjustment and after the adjustment. As you can see, for the 1st January flooding event, the RMSE is reduced to 32 up to 33% of domain-wide the RMSE. Meanwhile, during localized rainfall or little to no rainfall detected by the GSMAP, as you can see in the figure, is from the middle of January, the RMSE could be reduced up to 80%. So for the conclusions, combining the advantages from satellite-based precipitation and observation could provide a more realistic spatial distribution of rainfall and intensity. This is proven by RMSE calculated before and after adjustment process could reduce the domain or the area bias from 30% to 80%. These are the references we used in this paper. Okay, thank you for your kind attention and see you.